Hello everyone, welcome to Signal Systems and Signal Processing with Wolfram U. The topic of this lesson is sampling. In this lesson, we'll go over sampling, which is basically the operation that leads to a representation of a continuous time signal by a discrete time signal. The most common form of sampling is known as uniform sampling, which basically means that the samples of the discrete time signal are uniformly spaced on the time axis. The spatial distance or the time delay between samples is known as sampling interval or sampling period, and the inverse of sampling period is called sampling frequency or sampling rate. The sampling theorem or the Shannon sampling theorem is a very important theorem in signal processing. It basically gives the conditions under which a sequence of samples completely captures all the information in a band-limited continuous time signal. Given a band-limited signal x of t, where the Fourier transform of signal x of t is equal to 0 for frequencies larger than some omega max and smaller than minus omega max. The Shannon sampling theorem states that the signal x of t is uniquely determined by its samples x at kt, if and only if it is sampled at a sampling rate omega s greater than twice the highest frequency of the continuous time signal, or the omega max. Denoting the sampling rate by omega s, the sampling period will be 2 pi over omega s. And 2 times omega max is called the Nyquist rate. So the Shannon sampling theorem states that if you sample a signal x of t at a sampling rate higher than the Nyquist rate, or 2 times omega max, you can completely reconstruct the signal x of t using the sampled signal. As an example, given the continuous time signal x of t as defined here, let's find the sampling rate and sampling period as discussed by the Shannon sampling theorem. Since cosine of 2 pi is a band-limited signal with maximum frequency 2 pi, that means that we can apply the Shannon sampling theorem. According to the sampling theorem, the sampling frequency omega s must be strictly greater than twice the signal's maximum frequency. So in this case, omega s must be greater than 4 pi. And the sampling period defined as 2 pi over omega s must be less than 1 over 2. Let's say we pick a sampling period of 1 over 3, which is less than 1 over 2. Then we'll have the sequence of samples shown here for t between 0 and 1. The plot here shows the original signal cosine of 2 pi t and the sequence of samples. To better understand the conditions for the sampling rate imposed by the sampling theorem, it is important to look at the Fourier transform of the sampled signal. Given a continuous time signal x of t that is band limited to omega max radian per second, sampling the signal x of t at a rate of omega s is basically multiplying the signal by an infinite impulse train, omega t of t as shown here. When we say an impulse train, it's basically a series of unit impulses repeating every t seconds, t being the sampling period, as shown here. So the sampled sequence x delta t can be simplified as the summation shown here, which basically, as shown here, is a impulse train with amplitudes equal to the amplitude of the original signal at every sampling point. Now that we have the definition of the sample sequence, we can take the Fourier transform of the sequence. Multiplication in time domain is mapped to convolution in the Fourier domain. Substituting the expression for the impulse train and evaluating the convolution, we get the expression shown here. If we expand the summation, what we have is that the spectrum of a sample signal is basically a superposition of shifted copies of the spectrum of the original signal. Now that we have computed the Fourier transform of the sampled signal, let's see what happens to the sampled signal in the Fourier domain for different values of the sampling rate. So given the signal x of t and its Fourier transform, we can plot them to see how they change over time and frequency. On the left-hand side, we have the original signal, and the right-hand side, we have its Fourier transform. Now let's look at the sample sequence. The plot of the sample sequence is shown on the left, and the Fourier transform of the sample sequence is shown on the right. As we just saw, the spectrum of the sample sequence is a superposition of shifted copies of the spectrum of the original continuous time signal. What we are seeing here is that if we sample the signal at sampling rate equal to the Nyquist rate, or 2 times omega max, the Fourier transform will be in the form of a contiguous spectrum. But when we increase the sampling rate, or basically decrease the sampling period, the copies of the Fourier transform of the original signal move further apart from each other. And for sampling rates smaller than the Nyquist rate, they basically overlap. This phenomenon is what we call aliasing. To better understand aliasing, let's look at the signal x of t defined as cosine of t, and let's sample the signal at two different sampling frequencies, one above and one below the Nyquist rate. So again, we need to look at the Fourier transform of the signal, the cosine function, and that is basically a pair of impulses. Here you can see a plot of the signal in time domain and the Fourier transform in frequency domain. For the sampled signal cosine of omega 0 kt, where t is the sampling period, the general formula for the Fourier spectrum is shown here on the right-hand side. Omega 0 is the fundamental frequency of the original signal cosine of omega 0 t, and omega s is the sampling rate. Setting the fundamental frequency omega 0 to 1 radian per second, we consider two different sampling rates. First, omega s is equal to 3 radians per second. In this case, the Fourier transform of the sampled sequence will be as shown here. If we expand the summation, you can see the exact expressions for the impulses inside the summation. We can plot the sampled sequence x of t and its Fourier transform on the right-hand side, where each pair of the impulses are shown in different colors. Now let's look at the sampling frequency omega s 3 over 2 radian per second, which is smaller than the Nyquist rate. Taking the Fourier transform of the sampled sequence with the new sampling rate and expanding the summation, you can see that frequencies in the sampled signal now masquerade as lower frequencies than in the original. For example, the original frequency omega may now manifest itself as frequency omega s minus omega, which is smaller than omega. This is what we call an alias, and the frequency omega s minus omega is called the apparent frequency. For this example, as you can see, we have aliases at frequencies 1/2 and negative 1/2. Let's hear aliasing in an audio of a sampled sinusoidal signal. Let's play 1 second of the audio of a sinusoidal signal with frequency shown here, sampled at a sampling rate of 8,000 samples per second. We can also look at the power spectrum of the audio signal, A1. Now we sample the same sinusoidal signal at a new sampling rate of 2,000 samples per second and listen to the audio again and note the difference. And again, looking at the power spectrum of the audio, you can see that the alias frequency now manifests itself at the apparent frequency equal to f of s minus f0, which is equal to 791 Hertz, the difference between the sampling rate basically and the fundamental frequency. Let's look at a different example. Assume that we have the continuous time signal x of t, which is not band limited. Let's sample the signal with a sampling period of capital T and check the Fourier spectrum of the sampled sequence. We already know the Fourier transform of the original continuous time signal as shown here. We can plot the signal x of t and its Fourier transform to get a better idea of what the signal looks like in the time domain and in the frequency domain. Now, the sampled sequence sampled with the sampling period of capital T, and the Fourier transform will be a superposition of shifted copies of x of j omega. Let's check the plot of the sample sequence and its Fourier transform as shown here. To avoid the distortion that you see here caused by the alias frequencies, we perform what's called anti-aliasing, where we pass the non-band limited signal first through a low-pass filter to suppress the frequencies larger than 1/2 of the sampling frequency before we start the sampling process. The process of reconstructing a signal from its sampled version, either exactly or approximately, is what we call interpolation. It's basically the operation of fitting a continuous signal to the set of sample values that we are given. The ideal interpolation, and by that we mean the perfect recovery of the original continuous time signal from its sample values, occur if and only if the conditions of the sampling theorem are satisfied. When interpolating, we basically pass the sampled signal through an ideal low-pass filter in the frequency domain. An ideal low-pass filter, as defined here, is an ideal interpolator, meaning that it reconstructs the original signal exactly at all points on the real domain. It has the cutoff frequency omega c equal to 1/2 of omega s, the sampling frequency, or pi over t, the sampling period. So in time domain, we will have the impulse response of the ideal interpolator as a sinc function. In other words, ideal interpolation in time domain is the process of convolving the sampled signal with a sinc function. For example, given the samples shown here and the sampling period of 1, the original signal can be constructed as shown here. We can plot the sinc functions corresponding to each of the samples, and the sum of these sinc functions give the original signal as shown here. Let's look at another example. Given the sample data values shown here, let's find the original continuous time signal x of t. The sampling period is 1. For ideal interpolation, as we just discussed, we reconstruct the signal x of t by convolving the sample values with the sinc function as shown here. For given sample values, here is a plot of the sample sequence together with the original signal that is reconstructed. The ideal interpolating function, as we define, has infinite support, and so it cannot be used in practice. All practical interpolating functions or kernels have finite support. Here are some typical examples. Interpolating with finite support kernels follows the same formulation as in the case of ideal sampling. Instead of convolving the sample sequence with the sinc function, the convolution is done using the kernel function phi as shown here. The interpolating kernel phi has local support and it has the important property shown here. It is equal to 1 at k equal to 0, and for all other values of k, it is equal to 0. Sometimes also we normalize the interpolating function so that the area under the curve is equal to 1, as shown with this integration. Here, r is the radius of support of the interpolating kernel. Here we show the result of practical interpolation, non-ideal interpolation using each of the interpolating kernels mentioned here. In this lesson, we covered the concept of sampling in signal processing, which is used to convert continuous time signals into sequences suitable for discrete time processing. We studied Shannon's sampling theorem in some examples of sampling with different sampling rates, and the related concept of aliasing and its effects were discussed. We also gave details of the operation of interpolation.